that says 0.025 over here, that says 0.975 up to that point. So if I want to find that upper value, that's going to be, I'm going to look for 0.975, which is going to be closest to this value right here. So that's 1.96. Okay? So Z alpha over 2 for the confidence interval is 1.96. But for the confidence bound, I need Z alpha. If I'm looking for a 95% lower confidence bound, that would be saying, okay, we're looking for the value so that 0.95 of the area is above. Okay, so I go to my table, my lower table. If I wanted to, I could also go for the upper table. It actually doesn't matter. We'll show that in a second. So that turns out to be between these two values right here. That's 1.64 or 1.65. We could go halfway in between and say 1.645, but I don't care. You can round to 1.65 if you like, whatever you want. Okay. So the alpha value is 1.645, and you might say, well, we said the negative value, but that just is taken care of in subtracting on the lower confidence bound. Okay. Just make sure for the lower confidence bound it's below your sample mean. For the upper confidence bound it's above your sample mean. Don't worry so much about plus or minus.
Why do we use the Z alpha in different cases
Why do we use?
I would have done Z 95%, not 0.
So that would be correct in a lower confidence bound. Okay, but why in a confidence interval is because the 95% is in the middle. Okay, that leaves 0.05, your alpha is 0.05. It gets split in half across the two tails. You get 0.025 right here and 0.025. That's why our formula is Z alpha over 2. Okay, that's where the alpha over 2 comes from. It's splitting that uncertainty in half. You've got 5% uncertainty that it falls outside of the interval. But that's half of the uncertainty that it goes below and half of the uncertainty that it goes above. For a confidence bound, it all gets pushed to one side. So you'd be right in that case. But for a confidence interval, it's split in half.
If I was calculating, well, I wouldn't be calculating the upper bound, I'd just be calculating the lower bound. If the upper bound, you're just calculating it all, right?
Yeah.
Oh.
Hey, Grayson.
I was wondering if you could talk about like the differences in calculating the Z confidence interval, the T confidence interval, and the confidence interval proportion.
Yeah, okay, let's talk about that. Well, I'm discussing when we use these, we've got 3 different confidence interval formulas now. Okay? So let's talk about all 3 of them. Let's see if I can find the scratch. So we have 3 confidence intervals. Okay. So the first is a Z confidence interval for a mean. It's x bar plus or minus Z alpha over 2 times sigma over the square root of n. We've got the T confidence interval for a mean. T alpha over 2 n minus 1 times s over the square root of n. And then the third is the confidence interval for a proportion. This is p hat plus or minus z alpha over 2 times the square root of p hat times 1 minus p hat over n. Okay, and this is really the traditional confidence interval for a proportion. We also talked a little bit in class about the score confidence interval for a proportion, which is that really complicated formula that I can't even write down off the top of my head. Okay, you're not going to have to execute that, you should be familiar with that there is some other better confidence interval or whatever that's more complicated to calculate. Yeah, you should know that that's the one that you're sort of like supposed to use in the real world. That's more accurate than this one, but you wouldn't ever have to actually do it on the exam. Okay? But, right? So when do you use each of these three? Okay? So here, these both have to do with a mean. Okay? This one has to do with a proportion, p. Okay? This is the mean of some variable from the entire population. This is the proportion of all individuals with some characteristic from the entire population. Okay? So a proportion comes up in a binomial setting when our individuals are being asked a yes-no question. Okay? All of our experimental units, okay, does this airplane have a specific defect? Okay, yes or no? Okay, we're going to be looking at really a group of an entire group of airplanes. Do each of these airplanes, what fraction of these airplanes have a specific defect? But each individual, we're asking a yes/no question. All right. The mean is when we're taking the average for an entire population. Right. If I'm asking what is the mean weight of all of these airplanes, okay, then I'm going to be dealing with a mu instead of a p. Right. So let's look at some examples from these exams. Okay, so this is from one of the exams. This says an environmentalist collects a liter of water from 31 locations along the banks of Ellerby Creek. He measures the amount of dissolved oxygen in each specimen and observes that the mean oxygen level is 4.62 with a standard deviation of 0.92 milligrams of oxygen per cubic centimeter of water. Okay? So here, we're clear, it mentions a mean. It's going to mention the sample mean specifically. Okay? So it's something that's quantitative. Right? Here, we're dealing with a mean. Okay? It's one of those two confidence intervals. We'll talk about how we distinguish between those two there in a second. If we look at so this question, number 2, from I think spring 2018 exam, says many modern psychologists and therapists encourage the use of mindfulness in the form of mindfulness-based cognitive therapy. 145 patients within the U.S. healthcare system who are in remission or recovery for major depression were treated for being randomly selected for the study. 57 of the patients relapsed into major depression at some point in the 2 years following the treatment. So here, we're asking a yes-no question. Did this patient relapse into major depression or did they not? Okay? That indicates that we're talking about a proportion. We're interested in the fraction of patients that relapse. Okay? So, that's the first thing that you should identify. Am I dealing with a mu or am I dealing with a p? Okay? Then, if you're dealing with a mu, you need to determine whether you use a t or whether you use a z. Okay? And this comes from the difference. The reason that we use t is because we're using s here instead of sigma. Okay? In the first case, this is a known population standard deviation. Okay, or known population variance. Okay? Here, the population standard deviation is unknown. It comes from the sample. Okay, so we estimate, so we know sigma. Okay, we know the true variability. But this example is just really kind of, it's an example for illustrative effect within, right, really just the bounds of introductory statistics courses. Okay? In real life, you're always going to use you're always going to use this confidence interval, okay, where we estimate sigma from the sample data using S. That is the sample standard deviation. Okay? Why the difference? Okay, this is really answering the question of why we use a t confidence interval, why we use the t distribution, which is why we have these two confidence interval formulas. Why I want to talk about both of them. Okay? Why do we use the t distribution? The t distribution adjusts for the fact that S might not be totally right. Okay? S is based on a sample, it's subject to uncertainty. In the same way, the sample mean is subject to uncertainty. Right? It doesn't perfectly reflect the population mean. It's not all that surprising if I get a bunch of people to take a bunch of samples of, oxygen content of the water in Ellerby Creek, and their sample means differ from individual to individual. Similarly, the sample standard deviations are going to differ from individual to individual. Okay? So they can't all be right. On average, they're right. Okay? The expected value of S is sigma. Okay? But they're not all right. So we have to account for that extra uncertainty from that S right here. So that's why we use the t distribution. You should be familiar with the relationship between the t distribution and the z distribution. How do the t distribution and the z distribution compare? Yeah, you remember?
Is it like on the T chart, if you look at the value towards infinity, it's the same as the Z chart?
Yeah. So the value towards infinity, you're talking about the degrees of freedom. Okay? As the degrees of freedom, as the sample size gets larger and larger, so the limit as n goes to infinity, if you look at your t critical value, it's going to approach a z critical value. Okay? But how does it compare? Are the t critical values bigger or are the t critical values smaller? Yeah. T critical values are bigger. Why does it make sense that they're bigger?
Because you're less certain of, basically you're just less certain of where the signal will end up.
Yeah, exactly. You need a wider net because you don't really know. You're adjusting for the fact that you don't actually know how wide your net has to be. Okay? So S might be a little bit wrong. Okay? It might need to be a smaller value. Okay? So the t critical values are larger than the z ones, the corresponding z ones. And what that means in terms of a picture, if I look at a t distribution and I compare it to a z distribution, both of them are bell curves. Okay? Here's the z distribution. Okay? It's centered at 0. T distribution is also centered at 0. Okay, this is a t distribution, also centered at 0, also looks like a bell curve. I can't really draw, an accurate comparison between the two. They both just look like bell curves. But comparatively, the t critical value has what we call fatter tails. T distribution has fatter tails. Okay? And remember how the t distribution comes up. Where it comes from is taking the sample mean, standardizing, but instead of dividing by sigma over the square root of n, you're dividing by s over the square root of n. You're dividing by the sample standard deviation, the standard deviation that comes from your data. Okay? Comes from the same data that tells you what the sample mean is, rather than the true value, the truth, the thing that comes from the population. So there's a good question, this was a very hard question about QQ plots from an exam last semester, if I can find it. Okay. This was this question right here. Oh, yeah, sorry.
I just have one question going back to the notes.
Yeah.
So if the value of t is greater, does that mean the peak of the actual graph go up higher too?
The peak actually has to be lower, because remember that the total area under the curve is 1, right? So if it's wider, right, the graph is more spread out, okay? You're more likely to get values on the outside. That means you're less likely to get values in the middle, okay? But the total area under the curve still has to be 1. So yeah, the peak ends up being lower. I wouldn't worry about so much about like comparing the peak values, but that is like the accurate way of doing it. Okay. All right. Okay. So, but this question was a good question about the t distribution and its relationship to QQ plots. Okay. Really hard question. It is known that the height of adult American males is normally distributed with a population mean of mu is 69.1 inches. But I don't know what the population variance is. I don't know what sigma squared is. Okay? If I select a bunch of random samples of size n equals 3 from the population of American males, and I calculate the sample mean across those 3 individuals, and the sample standard deviation for each of them, and then I standardize a bunch of values. But I standardize using s instead of sigma. We're asked which of these QQ plots would correspond to this data set. So then we've got the sort of, we've got 5 different QQ plots right here. And the question is which one is it? So I'll tell you if instead of s, I use sigma. Right? If we did x bar 3 minus 69.1 divided by sigma over the square root of 3, that's a z. That's a normal distribution. That's going to be A right here. This guy would be given by A. But when I divide by S instead of sigma, when I'm using the sample standard deviation across only 3 individuals, S might not be a very good estimate for sigma. So we might be wrong about these values. So then, this is going to be a T. Now the question is, if that's the case, which of these QQ plots would this data look like if it were a t distribution instead?
D.
Sorry?
D.
D. Why D?
It's approximately normal.
I mean, I don't know that it's any more approximately normal than the rest of them. So D would be, this would be the case. It's concave down. This is going to be negatively skewed. Okay? I don't actually see any reason for this to be negatively skewed or positively skewed. So D would be negatively skewed. C would be positively skewed. This doesn't seem like there would be skew in any direction to me. Okay? But the question is what would happen?
More value spread to the tails.
That's exactly right. More values would be spread to the tails. So which QQ plot is that?
E.
You gonna say E? It's B. Okay? So E is bimodal. Okay? E, this one is the bimodal distribution. We've got sort of 2 lines right here. We've got 2 peaks, okay, for a bimodal distribution. Okay? B, this is the correct answer. Remember, this is the one that we saw. In the middle, things look fine. Okay? In the middle, it looks like a normal distribution. What happens, though, is we get, just like you said, more extreme values. We get more values that are spread to, the tails are spread out further. And so we get outliers, more extreme outliers. That's exactly saying that we've got more probability in the tails. Okay? So that's why B is the answer. It's a really, really hard one. Okay. Another hard QQ plots question is the following one. And to be honest, this one, I don't know, it's good for us to look over, but it was a little bit more obvious semester I gave this exam. Oh, it's on the back page right here.
We,
Yeah.
we calculate S from our sample, samples,
Yes.
right? So will we be calculating S in the test?
You won't have to calculate S yourself.
Okay, so you'll tell us what S is.
I'll tell you what S is. We know what I've given you the formula for S, and actually I think you used it on the very first day of class or whatever. You calculated the sample standard deviation, but I'm not going to actually ask you to repeat it. But the formula, maybe it'd be good to recognize it, but S is the square root of the sum of the x's minus the sample mean squared, the standard the deviations divided by n minus 1. That's the sample
So
standard.
I'm just confused why, if we're already given S, what's the difference? What's the difference going to be when we calculate it? Because we're given S, which is approximately standard deviation.
Mm-hmm.
Oh wait, T, never mind.
Okay, yeah. Alright. Alright. So, okay, so B is, this one's another hard one, but it was a little bit easier this semester. It was given because there was group fun that was related to this question, but we'll think about it anyway because it's a good exercise for QQ plots, okay? So the lifespan of a light bulb produced by a particular manufacturer follows a distribution with a population mean of 12 and a population standard deviation of 11. We've got light bulbs that are selected in a simple random sample and their lifespans are measured. Which of the QQ plots would correspond to this data set?
I have a question about the last one.
Sure, yeah, let's go back to the last one.
Did you make any actual connection with the Z distribution, or did you just write it down to prove that it wasn't that because you have the S?
Yeah, this was in comparison. I was just saying,
So if you're giving us something like that and we see that formula, we're just going to know that it's a T distribution because there is an X,
yes,
right?
exactly.
And then we can directly recognize that since it's a T, then it's going to have extreme outliers on the outside
Yes.
because it is a lower curvature.
Yes,
Okay, great.
yes, you're exactly right. Alright, so this one, important things are mu is equal to 12, sigma is equal to 11, okay? And, right, so just because we know mu and sigma though doesn't mean that we know it's normal because we're not standardizing here. We're not doing any kind of simple central limit theorem mumbo jumbo where I take x bar minus mu divided by sigma over the square root of n. We use large sample size. Here we're just talking about the individuals, okay? But we're comparing, we know what the mean is, we know what the standard deviation is, and we're talking about light bulbs right here. What characteristic of the QQ plots? Okay, so the QQ plots, A was the normal one, okay? B was symmetric with outliers. This was like a T distribution. Outliers. C was positive skew. D was negative skew, and E was bimodal. And the question is, if we have a data set that looks like this, which of these would it be? What was that, Spencer?
Negative skew?
Negative skew. Why do you think negative skew?
That's right. Isn't it like all your data sets on the positive side is negative skew? I just want to make sure that's right.
So you got it backwards. It's actually positively skewed.
Okay.
Yeah, but I think you're thinking in the right direction. Okay. So what Spencer's saying is, hey, look, this is we're talking about the lifespan of light bulbs. It was Spencer, right? That's right. Okay, cool. I just wanted to double check. Okay. So he's saying, hey, look, our data is positive. It's the lifespan of a light bulb. It can't be negative. But we've got this large mean, we've got a mean, and the standard deviation is really large relative to the mean, okay? And here, right, if we're getting all of this variation, we're supposed to be able to get sort of a large standard deviation relative to the mean. We can't go very far in the negative direction. The variation has to come from the outliers on this end, okay? It has to come, I mean, think this, really we talked about the lifespan of light bulbs using exponential distribution, right? Those were positively skewed things. Because, right, we've got this really large standard deviation, but it can't be symmetric, okay, because it can't be negative. The lifespan of light bulbs is positive. So this one ends up being positively skewed. It has to have a distribution that looks like this. That's the top one.
So that picture means positive.
Yeah, this picture means positive skewed. Yeah, and then C was the easy one right here. This one is negatively skewed. That's D.
And that's because there's things pulling the tail of the
Yeah.
so they're gonna be pulling towards the negative.
Yeah, the tail points in the direction of the skew. Yeah. So this is negatively skewed. Sometimes this is called left skewed. The other direction is positively skewed. It points in the positive direction. Sometimes that's called right skewed. Okay? But the tail tells you the direction of the skew. Alright. That's technically all the time I had budgeted. I'll hang around though if you have. Yeah, you still get a note card. One side of a 3x5 inch note card. Okay. Yeah, the continuity. Okay. Yeah, let's talk about the continuity. We have a binomial ring. Okay. This is like, okay, the number of free throws I'm hitting. Okay. And sample size, how many free throws I'm shooting. All free throws are this. And we talked about it, the sample size is large enough that it is performing. Okay? Approximately normal. I expect that I'm going to hit any kind of bid rate, like 80% of the throws I'm going to multiply NNT. That's my expected value, NNT. And then we have the formula for the variance, which is NP times 1 minus. Okay? So if I'm looking at the probability x is less than or equal to 30, then I might say, oh, well, I'm just going to use this normal approximation, I'm going to standardize. Okay? I'm going to change this to a z. I know what the expected value is. I know what the standard deviation is. So I'm going to take x minus np divided by the square root of np times 1 minus p. I'm going to do the same thing on the other side. Okay, square root of np. Okay, and this turns this into a z, approximately. Okay, so now I get this number and I look it up in my z table. You tell me exactly what it is. Okay, but the thing is, this is a discrete random variable. Okay, so if I look at the number of free throws, has to be that I make is less than or equal to 30. This is the same thing as saying the number of free throws that I make is less than 30.5. Right? Because I can't make a half a free throw. If I make less than 30 and a half free throws, I make less than 30 free throws. And it's the same thing as the probability that x is less than or equal to 30.99 as well. But the thing is, I could do, these things are equal, I could just as easily have standardized using that guy instead. But if you look that up in a table, you'll get a different value, right? You're going to get a different value if you use 30.99. You're going to get a different value if you use 30.55. You're going to get a different value if you use 30. Because z is a continuous variable. It cares. Z actually cares whether you use 30 or 30.5 or 30.99. A binomial doesn't care, right? It doesn't care because it's discrete. So the question is which of these values is the appropriate one to use? Okay? And then that's why you just meet in the middle. So you do the middle value. Okay? You got to be a little bit careful because you don't always. So you use 30.5 right here. You got to be a little bit careful because you don't always add 0.5. Sometimes you subtract 0.5. So, and there are two ways to get around it. Okay? One, so let's say we change this to greater than or equal It's not true that the probability that x is greater than or equal to 30 is the same as the probability that it's greater than or equal to 30.5. Because if I've hit at least 30.5 free throws, I can't hit 30. And I've hit more than 30. I've hit at least 30.5. So now, this is not true. I change this to 29.5 or 29.99, okay, or something like that. Okay. So when I'm doing greater than or equal to, I have to actually subtract 0.5 instead. Okay, so you just have to be careful of that.
And so when do you know to like add, when to add the 0. I just meant the 0.5 when the other binomial is bigger?
Yes.
Like let's say that with question, you can understand the figure out.
Yeah. So anytime we're dealing with a binomial distribution for this test, we're not using the discrete binomial distribution. So it is going to be normalized here. On like the final or something like that, it could. And there's a problem on here, question 7 from one of the exams, from exam 1 spring 2019, where you do both. And it says there, like, it says approximately. It says tell me the probability approximately, and that's an indication we're going to use the normal approximation. And also, the sample size is n equals 100. And if you look it up in the table, there's no n equals 100 in the table.
Okay.
Or if it's a weird value like n equals 27. There's no n equals 27 binomial table. It's only like 5, 10, 15, 20, 25, 50, something like that. So if it's not one of those, you can't use the binomial table. You're going to have to use the normal approximation. Okay? Cool. What's up, Randy?
For the S,
It is Randy, right?
yeah, it is.
Okay, cool.
That makes sense. I'm just like, I'm not comfortable with that.
You would never have to calculate it by hand. If you wanted to, you add up your values, subtract off the sample mean, divided by the sample size minus 1.
Regarding COT and the normal approximation binomial, the fundamentals for that, how far back?
I would just look at the CLT section or whatever. I wouldn't look back any further than the CLT in the notes.
But to understand the
Well,
COT.
maybe the level of attacks.
Yeah, I don't. I mean, you should be familiar with the normal distribution, I guess. You might need to familiarize yourself with how to calculate normal probabilities. That's the main thing.
What about the binomial?
Binomial, I mean, you should recognize a binomial setting. So you might need to remember when a binomial comes up. And that's when you've got a fixed number of trials, you're asking a yes or no question, or there's success or failure. All the trials are independent.
Alright,
Yeah, you can email me. I'll try to respond.
actually, kind of related to this, so what if it's not greater than, or if it's just greater than?
If
Does
it's
that make a
greater,
difference?
yeah. So if it's greater than, well, there's a couple ways that you can do this. Okay. So my recommendation is just to always find the sort of like half integer for which this is